Okay, so we're speaking about synaptic communication here. And so we're talking about what's happening on the end of this first neuron, and then what the effect that's brought about on the effector cell is, okay? So this is a presynaptic neuron. And this is a postsynaptic neuron, or an effector cell, okay? And so basically we have the action potential moving along here. Let's actually put a few structures here first. So we know in the axon terminal, we have some vesicles. We have quite a few vesicles here. On the membrane of this axon terminal, we have voltage-gated calcium channels. Right. Let's label this here. This is a voltage-gated calcium channel. Right. We know we have a receptor here on the postsynaptic membrane. So this is a receptor of some sort. We also know we have this Pac-Man type molecule, or type enzyme, sorry. Okay, and then we have this reuptake molecule here on the other side. Okay, that's our reuptake molecule. Alrighty, so the action potential we know is coming down in this general direction, moving along these voltage-gated sodium channels. And when it gets to the axon terminal, it's going to depolarize the membrane. So we know that at rest, the neuron is going to be negatively charged inside. But when the action potential gets here, right, so it starts out negatively charged. When the action potential arrives, it becomes positively charged. Okay, so it's going to excite the membrane here. And then that is going to open up these voltage-gated calcium channels. Okay, as a result, calcium is going to rush into the membrane here. Okay, calcium rushes into the membrane, and that actually triggers these vesicles, right? These vesicles with a neurotransmitter in them. Right, so they got some neurotransmitter. And when calcium rushes into the membrane, because these voltage-sensitive calcium channels have now opened up, this triggers the exocytosis of these vesicles. So we talked about this process called exocytosis, where the membrane of the vesicle fuses with the membrane of the terminal bouton, and then the neurotransmitter is dumped out into the cleft, okay? When this dumps out into the cleft, it's going to bind, again, very specifically to its receptor here, and binding to this receptor will eventually bring about some cellular response. Okay, we'll talk more about what this is towards the end of today. Okay, but don't be focused too much on this. So the binding happens, and that brings about some sort of cellular response on the second neuron or the second cell. Now, in the meantime, there's still some excess neurotransmitter hanging around here at the cleft. And so that's the purpose of this enzyme. This enzyme is going to break down some of this excess neurotransmitter. Okay? So breaks down excess neurotransmitter. Okay? And then the second option, right, for the neurotransmitter that's not broken down is that it can be reuptaken into the axon terminal. It can be repurposed and repackaged into a new vesicle, and then it can be exocytosed again. Okay, so there are three options for excess neurotransmitter. Diffuses away from the cleft, so it just simply diffuses away. is broken down and then diffused away. So it's broken down by this enzyme, or it's recycled. Okay, it's recycled. And so just to review this one more time, just for repetition, the action potential gets to the axon terminal. We open up voltage-gated calcium channels. Calcium rushes into the membrane. Calcium facilitates the exocytosis of this vesicle such that the vesicle membrane fuses with the terminal Bouton membrane and the neurotransmitter is dumped into the cleft. Once in the cleft, the neurotransmitter binds to its receptor, its unique receptor, and then the receptor brings about some type of cellular response. Excess neurotransmitter can do one of three things. It can diffuse away from the cleft. It can be degraded by this enzyme and then diffused away from the cleft, or it can be reuptaken, repackaged, and repurposed, okay? And that is to facilitate the cessation of this signal. If neurotransmitter lingers at this junction, we will continue to propagate the signal because it will continue to bind to this receptor and it will continue to bring about cellular response. That's not what we want. The reuptake molecule? Yep, just brings them back into the membrane, puts them into a new vesicle, and sends them to the cleft again so that they can be exocytosed. But the important thing is that we must clear the excess neurotransmitter. Otherwise, this signal will fire indefinitely. All right, and that's going to give us spasticity in terms of our muscles and other dysfunction in other areas, right? We must cease the signal at the end of this, okay? And in doing so, we have to clear the excess neurotransmitter. Okay, any questions on this? Any other questions on this? I want you to really practice drawing out these sequence of events. Practice writing down these steps. Again, we're going to see this when we look at muscle. This is the mechanism of how muscle contracts, so to speak. We're going to see this when we look at the autonomic nervous system, right? The innervation of cardiac muscle, the innervation of smooth muscle. This is how that signal is passed, right? Irregardless of what that second cell is. This could be adipose, this could be muscle, this could be glandular tissue. This is how the signal is passed, okay? And we call this chemical because obviously we're using chemicals. We're not actually using electrical signals across here. So the electrical energy of the action potential has been transmitted into chemical energy that crosses the synapse as a chemical, right, neurotransmitter. At the postsynaptic membrane, this can now be retransferred into chemical energy and propagate along the neuron if it's a second neuron, or it can bring about some other cellular response. Okay, so the chemical electrical transmission is very important, and that's why this is not an electrical synapse, it's a chemical synapse, because the movement across here is via chemicals, okay? All right,